Thank you very much for having us, Gutia. First of all, I hope everyone is keeping well and is safe during COVID. Um, we're really grateful to be here for a number of reasons, but one particular reason is that as we were going through the academic literature and trying to figure out what kind of tools we should build for our package, we came across a number of really good papers written by Gutia, and in particular a paper on what was the most cutting edge for in terms of like hierarchies, networks, correlations, and measures of codependency in finance, and this really like provided the roadmap that we've been working on for the last 6 months, so that what I found in industry was just that people were time and time again, if I go to a job interview and I'd see like, oh, they're implementing this portfolio optimizer, and I'd go to another job just down the road here in London, and I would interview, and they were struggling with the same problem, and often it was like a problem I had coded up like 3 or 4 years ago. And so often in finance, what is happening is everybody's just kind of like rebuilding stuff over and over and again, rather than having like one central location of like tools and techniques that they can use really out the box, that didn't require like a lot of uptime to get using. So what I'm going to do, I'm going to share my screen and just give a very short presentation on Hudson and Thames, what Mlfinlab is, and then I'm going to hand over to the students and they will present. So let me share my screen here. There we go. Can everybody see my screen?
Yes, it's okay.
Perfect. So I'm Jacques Joubert, the CEO of Hudson and Thames, and I'm busy leading this very new organization / startup. To start off with, Hudson and Thames is an engineering company that helps portfolio managers and traders who want to really leverage the power of advanced algorithms. And we do this by providing reproducible, interpretable, and easy to use tools. Our flagship library is called Mlfinlab, which is short for Machine Learning Financial Laboratory. And we really believe that adding it to your company's pipeline is like adding a department of PhD researchers. Intellectual property is the most important asset that fund managers have. Now, imagine if your fund had the same resources and technology as the top funds in the world. What would you do with it? What products would you build? Now, I can't tell you that what these companies are using, but I can tell you that many of the top industry practitioners and academics publish techniques in elite peer-reviewed journals, techniques that we build. I can tell you that it's easy to see who these companies hire, what their PhD thesis was on, and who their supervisors were. It's quite easy to build a map of cutting-edge algorithms once you know what you're looking for. So this is a big one. Finance, we really believe needs an upgrade. So according to the CFA Institute, they conducted a series of surveys of modeling techniques among large asset managers in the United States and Europe. And they came back with this famous quote saying that linear regression remains the primary workhorse for financial modeling, being used by the vast majority of firms surveyed. Now, this is a strange statement to come to terms with. On the one hand, we have passive investors who believe that markets are efficient. And on the other, we have active managers whom the majority believe that a model as simple as linear regression is capable of exploiting billions worth of dollars of profit every single year. The truth is that most asset managers have failed to unlock the potential of advanced algorithms. Yet many of the top 10 funds in the world are data-driven, with both the largest Bridgewater Associates and the most successful Renaissance Technologies using advanced machine learning algorithms. So into Mlfinlab. Mlfinlab is a collection of production-ready algorithms from the best journals and graduate-level textbooks, all packaged into a Python library that can be easily installed into any research environment via the terminal, with the command as simple as pip install Mlfinlab. Once the library has been installed, an array of capabilities and new product ideas have been unlocked. You can now spend more time using these tools than reading papers about them and trying to implement them. We cover really a large range of algorithms, from portfolio optimization to model interpretability, frameworks for backtest overfitting, machine learning pipelines, all algorithms throughout there, and even some market microstructure features and features from the high frequency literature. So, we formed this community with academics, fund managers, and students, and it's really become our think tank and central location for people to collaborate and share the latest news and papers. Thankfully, one really good example of this is this Hong Kong machine learning meetup run by Dr. Marty, whose, as I mentioned, research we implemented with great help from him, the original author. And we really hope that these tools will go on to promote and further aid research in the field of financial machine learning. Next, we come up to our apprenticeship program. Our apprenticeship program is an intensely focused course that results in a portfolio of work through building expert knowledge, authority positioning, and tangible results. We focus on research projects, as I mentioned, within financial machine learning, and building tools which thousands of quants will use. For those of you who are interested, applications for our next cohort close on the 23rd of October, with the next batch starting on the 1st of November. Today, 3 of our students will be presenting: Uri Lee on networks in finance, Valeriia Pervushyna on optimal stopping in pairs trading, and David Munoz Constantine on synthetic data generation, and in particular, a special paper from Marty on core GANs. So without further ado, I would like to please welcome Uri Lee.
Welcome everyone. Today I'm going to be talking about network visualizations and methods. And to quickly introduce myself, my name is Uri Lee, and I've worked on creating the network visualizations module for the Mlfinlab package during the summer. And I'm a third year computer science student at King's College London. Today I'm going to be describing what some of the network methods are in finance, why we analyze them, and how you can use the Mlfinlab package to analyze some use cases. So first of all, why do we care about these network methods and why they're important? So we can use these methods as a means of looking at diversification potential, for example. So normalized tree length, which is essentially the average edge weight of the minimum spanning tree, is correlated with market returns and negatively correlated with risk. And all of these network methods can be used to create these kind of structures, visual structures, which correspond to underlying kind of sector groups, which can give you an understanding of what's going on. Another interesting aspect is that minimum spanning trees shrink during crisis, and I will talk a little bit about what happened during the COVID-19 crisis. And another interesting aspect is actually looking at central nodes versus peripheral nodes in the tree. So for example, in the case of the planar maximally filtered graph, if you compare the portfolios of central nodes versus peripheral nodes, you see that the peripheral nodes outperform the central nodes. So you can see how this can be applied for a long-short equity portfolio. And I highly recommend Gautier's paper, and written by others as well, on the review of all of these network methods. It gives you kind of a broad scope of all of the current kind of methods that have been used and how they were developed, and some interesting aspects. So I really recommend that paper. So first of all, what are networks in finance? So usually the nodes are quite straightforward because they represent the financial instrument, so typically stocks, bonds, or any type of instrument that you want to represent. But there are lots of different ways of representing the relationship. One way you can represent the relationship is to take the pricing data. So say for Microsoft and Apple, for a given time period, calculate the log returns and the correlation from the log returns and the distance between the nodes. So what you end up with is a distance between all of the nodes in the graph, which would lead to a complete graph, which would be too dense to kind of get any useful information out of. So how do we filter out the most important links? And one of the ways to do this is the minimum spanning tree. So the minimum spanning tree is the combination of the minimum edge weights, where every node is connected to another node by some path, and the resulting tree has no loops. So we can look at how to create an MST using the library, and I'm going to talk a little bit about the impacts of COVID-19 as a use case of how to use the library. So I will quickly show a notebook. So first of all, we can import what we need, and we just import the method generate MST server, and then a sample data frame. This is the sample of log returns. And the way you can generate the MST is to create a server, import the df, and we just pass the param Jupyter as true because then it works within the Jupyter notebook, which I'll show you in a second. So Jupyter server.run server, and then mode 9. So we can have a look at what happens. It's being a little bit slow, but oops. Okay. Let's run this. Oh, this port is somehow says I'm running this already. Just give me a second. Show you an external node then. So it's just I'm taking up the localhost port, so saying that I can't use that one. Oh, let me try a different port. Let's see. Okay, there we go. And this should work in mine as well. There we go. So as you can see, this is the visualization and it works within the Jupyter cell. And you can kind of like interact with the nodes and zoom in, and you can have the different kind of formats as well. And then this gives you like a summary of the overview of the MST. And it's just 4 decimal places by default, but you can change that as well. And because the MST usually kind of branches off, if you branches off with sector groups, not always, but sometimes it will kind of group together. What we can do is add the sector groups. So if we pass in a list dictionary, we can pass in the colors. And the market cap as well. So let's have a look. I need to run this. There we go. So yeah, as you can see, the industry groups shown by the color code, you can see that these kind of like display which group each stock is, and it's indicative of the market cap. And you can kind of put any values that you wish to. And another thing to mention, for bigger data sets, you can specify the algorithm. But obviously it gives the same MST, it's just going to be much quicker for larger data sets. And then we can go on to the COVID comparison of the MST. So I have a DF of log returns, and then I just slice it by the 3 periods shown. So I slice it by pre-decline, decline, and post-decline recovery periods. And then I can specify the sector groups, and based on that, we can have a look at what that looks like. Server, and let's start with the pre-decline period. And generate MST server will return like a dash interface, which you can call run server on. Mode, let's do inline. So yeah, this is the minimum spanning tree for the pre-decline period. And you can kind of see like which kind of nodes are the central nodes. So city group is like the central node for like the financials, energy, technology. And what's interesting is we can look at the statistics like the normalized tree length and see how that changes over 3 periods. This is the MST for the decline period. So what we can look at is, you can see that kind of JPM and Morgan Stanley, they become like the connecting structure of the MST instead of just being a branch. And interestingly, the normalized tree length decreases a lot. And those decline period as well. So yeah, you can kind of like go through the different periods and experiment with the nodes and look at like the statistics. And what's interesting from this is, yeah, so the normalized tree length, as I mentioned, is correlated with the market return and negatively correlated with volatility and tail risk. And from the general observations of looking at the MST throughout the periods, we can see that the COVID-19 crisis has shrunk the minimum spanning tree, as is expected during crises. And the distances between the node and the same category decrease. So it seems to just suggest that the market has become overall more correlated post-decline than pre-decline. Another method to filter down the graph is the planar maximally filtered graph. And the planar PMFG is a planar graph, so no edges can cross when drawn on a flat surface, where the edges connecting the most similar elements are added first. So for example, with correlation, you would add the edge with the highest correlation value. And the good thing about the PMFG is that it retains the minimum spanning tree as a subgraph, but has more information. So if you look at the green edges here, this is part of the MST, and the blue edges are part of the PMFG or non-MST part. And we can look at this constructing a PMFG. So you add the edge with the highest similarity first, if the resulting graph is planar, and you keep adding until 3n-2 edges have been added. So why do we analyze the PMFG? The PMFG can describe the underlying hierarchical structure of the network. So in the work done by Aste and others, they saw that the US interest rates grouped together by maturity. And for stocks, for example, it would group together in some sort of logical way, such as sector groups. So an interesting study done by Pozzi, Demete, and Aste, the researchers conclude that it's better to invest in the peripheries of the PMFG, as this leads to better returns and reduced risk. So in order to explore this, what I decided to do is create a portfolio based on the PMFG, selecting the peripheral and the central stocks. So the idea was to make investment at like the very top, right before the dramatic drop in the market, to try to understand our peripheral node portfolios more robust than central ones. And I kind of do the analysis, select the stocks before the drop, and then do the portfolio analysis to see if they are any better. So I can show you how I did that. So first we can make the imports and the data frame. So this time these are the closing prices of the stocks. And I can slice it for the pre-decline period. So we can do the portfolio selection and then calculate the log returns. Yeah, and the correlation and distance matrix. And to select the stock, so Pozzi, D'Amato, and Asti, they use this hybrid measure of the different centrality measures. But they mentioned that the peripheral nodes consistently outperform the central nodes for all centrality measures. So this is a variation of a centrality measure using Network X's library. And the factors included are like degree, betweenness, and a few others. So what we can do is import the method. And first we need to create the PMFG object. So based on the input distance matrix, PMFG, distance matrix. So the PMFG object will take in a distance matrix or a correlation matrix and output a planar maximally filtered graph. And then we can get the PMFG graph. So this is the network X's graph object. And we just have to call get graph. So, and then based on the PMFG graph, we can create the ranked nodes. PMFG graph. So what this will do is create a list by ranking of how central or peripheral the nodes are. So if we can plot it, I'll just show you. So what I do is take the top 10 and the bottom 10 of the list and then define it as the colors so we can have a look on the graph. So we call generate PMFG server instead of MST server for this one, and then take the log data frame. Jupyter is true, and the colors. Just run that. And I'll display it in external mode so you can see it better. Or is, just use this. Yep. So when you're running this outside of the Jupyter Notebook, you'll just get a port number like this. So yeah, you can see the color code as well. So for the highest rank, it's kind of in this deep or this purplish color, and the lowest rank, the most peripheral nodes are in this pinkish color. And you can see the central nodes have a lot more connection than say the peripheral node. This one only has 3. We can kind of look the different ones. Yeah, this one has a lot of connections in the graph. So because that minimum spanning tree isn't clear from this graph, we can also plot that as well to see how the peripheral and the central nodes look. Just call generate MST. Yeah, So as you can see, the peripheral nodes are they tend to be on the outskirts of the tree, and then the central nodes tend to be on the central kind of parts of the graph. So like connecting the different parts of the minimum spanning tree. So now we can analyze for the performances to see what happens. So comparing the PMFG portfolio performances, what we find is that the orange line is the peripheral stocks portfolio and the blue line is the central one. And volatility is consistently lower throughout the period. And for the Sharpe ratio, this is quite interesting because for the beginning half, the Sharpe ratio are more or less the same. But as we get kind of like July period, we see that the peripheral stock portfolio Sharpe ratio diverges from the central stock portfolio Sharpe ratios. And this is most clear from the cumulative returns graph, where the peripheral stocks portfolio drops less than the central stock portfolio, and it also recovers much quicker. So I think it drops around 8% less, and then it recovers to 90% of its value, or 90.7, whereas the central stocks portfolio recovers to around 76% of its value. So to conclude, in line with the research by Pozzi, Di Matteo and Aste, we see that the peripheral stock portfolio is less risky, recovers more swiftly, and is more robust in times of crisis. And that is all for today.
Okay, so today I'm going to be presenting on Ornstein-Uhlenbeck model, optimal stopping problem in pairs trading. A little bit of introduction on my part. My name is Valeriia Pervushyna, and I was an apprentice when I was developing this module, but currently I'm a full-time researcher at Hudson and Thames. And also I'm currently a master's student in the Quantitative Finance program at the University of Warsaw. My social media handles are mentioned down below. Also, I would like to mention that the following implementation and theoretical information closely follow the work of Professor Tim Lee in optimal mean reversion trading, mathematical analysis, and practical application. I greatly recommend you to check out his work. So without further ado, let's move on to the part one of our presentation, the theoretical background. If you're beginning talking about pairs trading, we have to start with mean reversion. Mean reversion is a financial term for the assumption that the stock's price will tend to return to the average price over time. And we know in the financial world is not a secret that some asset prices tend to be natural mean reverting, such as some commodities prices, foreign exchange rate, volatility indexes, some global and US equities, and also some processes are known to be modeled by the mean reverting processes, such as interest rates and default risk. However, the most interest for us as investors bring the pairs trading strategies, because they allow us to take advantage of the mean reversion quality while using other potentially non-mean reverting assets. And also it opens us the ability to use the statistical arbitrage. So what is our goal when we are creating a pairs trading portfolio? Our goal is to create a spread that emulates the behavior of a mean reverting asset. Our solution to this problem is a two-step process. The first part is choose a pair of highly correlated or co-moving assets, like you see on the screen on the right. We've chosen gold and GDX indices to be our example in this presentation, accordingly also to example in the book of Professor Lee. The next step would be long alpha amount of the first asset and short beta amount of second asset to create something that we will call now the optimal mean reverting portfolio. You can see the formula down below. But the question is, How do we choose the best ratio between the two assets to achieve the maximum goodness of mean reversion? And here, when Ornstein-Uhlenbeck process come into play. Ornstein-Uhlenbeck process is very famous in financial and physics world as the first choice of modeling the mean reverting processes. It is established by the following SD that you can see now on the screen. The parameters that we want to look on the most is first theta, long-term mean, mu, mean reversion speed, and sigma, the amplitude of randomness in the system. As we established our model now, let's proceed on to fitting the model to our data. The first step would be to maximize the average log likelihood function presented on your screen right now with respect to its parameters, theta, mu, and sigma. The second part, to find the optimal portfolio and hence the optimal ratio between the two assets, we set our alpha as constant and choose such beta as we vary through the different values of beta that will maximize our previously found max log likelihood function. The main strategy for trading the mean reverting spreads is rather simple. It's you buy high and then you sell low. But the main question still stands. When do we exactly as investors enter the market or decide to liquidate our position? Is it optimal to wait or do whatever we want to do immediately? And here's when the optimal stopping problem comes into play. Let's suppose the investor already has a position with a value process xt that follows the Ornstein-Uhlenbeck process. After closing the position at the time tau, he receives the value x tau and pays the constant transaction cost c. To maximize the expected discounted liquidation value, we need to solve the optimal stopping problem that will look like so. So here we can clearly see that we're trying to maximize the expected discounted value of the difference between the value we receive and the constant transaction costs that we pay. However, naturally, we can also think about the optimal enter problem as the future optimal value of liquidation minus current price and transaction cost constitute the cost of entering the trade. To maximize the expected discounted value of entry, we need to solve the second optimal stopping problem that looks like so. Also, sometimes investors would like to add the stop loss level, and if the price of a portfolio will ever reach this level, then the position will be closed immediately, so the problem will be reformulated in the following way, like so. So let's sum it up and understand better what our desired result look like. We got our testing data and we got our optimal entry and liquidation levels that we've achieved by training our model. Then the main incentive is to buy as soon as you reach the optimal entry level and sell as soon as you reach the optimal liquidation level. If we reformulate our problem with the addition of the stop loss, the incentive will change a little bit. First, we buy as soon as we reach the bound of optimal entry interval, and then also sell as soon as we reach the optimal liquidation level. The problem is formulated with the premise that we have our only one optimal entry and liquidation points that we will achieve the maximum value, safe maximum value from. So it is meant, this model and this module is meant to be a building block in a more larger complicated strategies and is aimed to be retrained. The model is aimed to be retrained and reused, but to do not talk about it too much and just show it to you, I would like us to proceed the second part of the module the module functionality. So we have the optimal mean reversion module structure that will consist of Ornstein-Uhlenbeck process, exponential Ornstein-Uhlenbeck, and Cox integral Ross submodules that were taken. They will be created by implementing the following chapters from the Professor Ming's book. But today we'll focus on Ornstein-Uhlenbeck submodule. We've set the following goals before us when creating and implementing the module. First, we wanted to make the tools to create the optimal mean reverting portfolio. Then, we needed the tools to fit the Ornstein-Uhlenbeck model to the given data. Then, to find the optimal entry and liquidation levels. Then we wanted to be able to showcase the results. And also, we wanted to additionally add functions for further research that will use the Ornstein-Uhlenbeck process. Needless to say, we've accomplished all of our goals, and I would like to welcome you to the introduction to the module. The first part for the introduction would be the global variables. We can logically separate it into three groups. First would be the Ornstein-Uhlenbeck model parameters that will consist of long-term mean reversion speed, amplitude of randomness, delta between the observations calculated in years, also optimal ratio between two assets, and the maximum log likelihood function value. Then comes the parameters that are used in optimal stopping problem: transaction costs, discount rates, stop loss level, then entry levels that will be calculated, and liquidation levels. And the last part would be the parameters that are described in the training data. We have the data parameters, that is about the training data provided by the user, and also the training period, the current training period that is chosen by the user. The most important thing is how exactly the user would interact with our module. So I welcome you to the OU model cycle, OU model usage cycle. Our first step during the interaction with the model is the model fitting. Then we proceed to the optimal levels calculation, then onto the data visualization. And if the person wishes, he might proceed to the model retraining when the cycle can repeat itself over and over again as much times as you would wish to. Let's look more in deep into our 4 parts. Starting with the model fitting. We use the fit function to do 3 tasks. First, settle the parameters for the optimal stopping problem, to find the optimal portfolio ratio, and to fit the OU model to the optimal portfolio. Finding the optimal portfolio ratio is mentioned as an optional part because you can provide the already created mean reverted portfolio of your choice, and it will still fit the OU model and calculate the optimal levels, even without the optimal ratio process. But if you were to give the 2 co-moving assets, as I've shown on the screen here, gold and GDX index, after using the fit function, we will get something that looks like so. This is our optimal mean reversion portfolio with the fitted OU model to it. Also, if you would like to clarify the training period or change it, like if you like to choose some specific training period from your given data, you can use the specification method and it will change your training period like so. It's only natural that after changing your training period, the result would look like that when it changes also. The important step is to understand how well the Ornstein-Uhlenbeck module even fits your data. To find out when using the check fit function, it will give you the output that will look like so. Our main incentive is to look and compare our average log likelihood functions And the simulated max log likelihood function has to be close to a fitted one. If the simulated max log likelihood function is much greater or unstable after a few usages, it means that your data provided to the model might not be good enough, and I would recommend you to maybe widen the training period or rethink the choice of your data. It might be just not well fitting enough to create an optimal reverting portfolio. The next step that our user would take is to calculate optimal levels. To calculate the optimal levels, we implemented 4 separate functions: optimal liquidation level, optimal entry level, optimal liquidation level stop loss, and optimal entry interval stop loss. After executing all these functions, we will get the results that look somehow like this. Also, we implemented the parameter check function to ensure of the existence of the solution to the optimal stopping problem. Because if your parameters are not good enough for the model to calculate your optimal entry or exit levels, the model will give you a sign with the warning that you need to change some specific parameters, like the stop loss level or your maybe discount rates or transaction costs, something like that. However, it's pretty much very robust, and I recommend you to play around with your stop loss levels and transaction cost of choice. Next, we proceed to data visualization. We can visualize the result in 2 ways. The first one would be to plot the optimal levels on the given data of choice with plot levels function, and it will look like so. You can recognize this output from the previous slides. Also, we have a choice to print all the parameters associated with our fitting model with description function. And it will look like so with all the statistics given, starting from training period to all the OU model parameters, and all the entry and liquidation levels will be stated in this in the output of this function. Then we can proceed to model retraining. If we would like to retrain our model on some different data or of a just different time interval, we can always retrain it with using the following functions: fit to assets and fit to portfolio. There is also a possibility to change the parameters related to optimal stopping problem along the way. So first, let me show you how the result changes when we refeed our data to some new data of our choice. It will give you such results. Mind you, there is no training period specified, and as we stated that our example stop loss level is none, all the functions that are related to calculation of levels with the inclusion of stop loss will not be shown. Also, we can also just change the specified training period similarly how do we do it in the fit function and get the results. You can see we get the different training period and also different values of all the parameters stated below. Lastly, but not least, let's continue to our additional functionality. The module also have the following functions to help the research that includes the OU processes in some shape or form. The function OU model simulation generates the synthetic OU process data, and you can do it 2 ways. First, if you've already trained your model, you can generate the Ornstein-Uhlenbeck process data based on your already fitted parameters, and it will look like so. Also, if you would like to set it by yourself all the parameters, you're also given this choice and the parameters, and the result would look like so. Also, we implemented the half-life function that returns the half-life characteristic of the fitted OU model. Let's finish up with the public functions overview. First, we have the part of model fitting in retraining with fit, optimal coefficients, fit to portfolio, fit to assets, and check fit functions. Next, we have optimal stopping problem with a function that gives us the expected discounted value of liquidation, optimal liquidation level, optimal entry level, expected discounted value of liquidation with respect to stop loss, optimal liquidation level calculated with respect to stop loss, and optimal entry interval calculated with respect of stop loss. We have our visualization and description part with description and plot levels functions, and also our additional functionality with OU model simulation and the half-life function. Thank you very much for your attention. If you have any more questions, I would be glad to answer.
Hello. Hi, everybody. Can everybody hear me okay?
Perfect.
Perfect. Okay. Awesome.
Good.
Thank you for attending this presentation on synthetic data generation and how to use Mlfinlab to augment your models. I'm just really quick about myself. My name is David. I'm an apprenticeship researcher at Hudson and Thames. I am doing my master's in computer science, focusing on artificial intelligence and machine learning at Portland State University. And my research topics focus on evolution strategies and specifically using differential evolution to optimize option strategies. And a really quick overview of this presentation. The first question that we need to answer is, why do we need synthetic data? Even though we live in an age of abundance of data, that most likely right now you can just Google Microsoft stock returns from 20 years ago and get your answer in a few minutes. So why do we need synthetic data? And after that, I'm just going to do an overview of our synthetic data generation module. I'm going to show you how to generate synthetic correlation matrices using the binds and extend and onion method, the hierarchical correlation block model, or HCBM, using different bootstrapping methods such as the row, pair, and block bootstrapping, and how to use Corgan. And also how to generate synthetic time series using again, the HCBM, the hierarchical correlation block model, and how to generate correlated random walks and how to discriminate their underlying distributions. So why do we need synthetic data? As I mentioned, you can just Google pretty much any stock returns and get your answer from Google or Yahoo Finance. So the main reason is that getting data that is reliable, bias-free, and complete, even just of stock returns, those data sets can cost thousands of dollars. And if you're a small trader like me, thousands of dollars is not something you can just buy here and there and do it all the time. And well, one of the reasons is, like I mentioned, if you just get your data from Yahoo Finance, you have no guarantees that it has been correctly calculated, for example, for dividends or for stock splits. Or even if there's missing data, you'll have to manually check everything, make sure everything is there. So that's why you could need historical data sets, but they're really expensive. The next reason is privacy restrictions. Financial data, for example, bank loan information from bank trading, they can contain sensitive and personal identifiable attributes of their customers. And due to new privacy laws such as GDPR, it is a little bit more difficult now to share that data between your team. You can just grab your bank data, put it in your shared drive, and just for anybody to grab it, you'll face several penalties for not respecting the privacy of your customers. The next reason is because historical data is inherently biased due to historical events only happening in one way. Just for example, as we have talked about the COVID crash this year. So what if you had a model that you wanted to be robust for the next COVID crash, right? It would be really easy to overfit for this event because it only happened once. So what if you can create multiple COVID type scenarios when you can stress test your model all you want? Then you have a guarantee that your model, well, you'll have more confidence that your model will do better. Probably not a guarantee, but you'll be more confident. There are many more reasons, as I mentioned, to reduce overfit. The more data you have, the easier it is to see if your model is overfit or not. There's, besides the GDPR, at least here in the US, we have different privacy laws such as FERPA and HIPAA that they don't just let you share the data with anybody or just as easily. Another reason is to reduce dataset imbalance. If you have one class of your dataset that's too small and you're able to generate more data for it, it will make your model more robust. And in general, just to be able to train more complex machine learning models, such as deep learning, it requires vast amount of information. So if you're able to generate as much as you want, you will be able to train this model more easily. And some of the challenges of generating synthetic data, the first, and I guess in my opinion, the most important one is to maintain the statistical and structural properties of the original data. It is not enough just to grab NumPy's random normal function and generate some data and call it a day, right? It has to be similar to the original data that you want to generate. And it also has to be fast to generate. You have to generate as many features and as many data points as you want in the least amount of time. If you have some algorithm that generates just a few data points in a few days, it wouldn't be nice to use it. It would just take forever and probably you wouldn't get anything done. And another reason to maintain privacy, as I mentioned, we have all the personal identifiable information, and just transforming your data is not enough to get rid of this, right? You cannot just do a standard transformation and call it a day because you can still track all the personal information. And our solution to this problem is the data generation module in Mlfinlab. It specializes in generating correlation matrices and correlated time series, and implements various methods from several authors that you can see in slides. And I am going to start with how to generate correlation matrices using the binds and extended onion methods. And just to recap really quick what correlation matrices are, they're constructed by using the correlation with stock returns over a defined time frame, and the Pearson's correlation coefficient is the most commonly used correlation metric. And something to keep in mind is the Pearson's only captures linear dependence between your data. So if your data has some dependence that is not linear, you'll have to use a different correlation metric. And actually, our model in Mlfinlab that is called the codependence module has a nice overview of different codependence measures that you can use if your data is not linear. So definitely recommend checking that out. And correlation matrices are useful for risk management, asset allocation, instrument selection, pricing models, you name it. They're a really important data structure in finance. So if we're able to generate them as much as we want, it will make our models more robust. And I will start with the binds method. So this method is a statistical and graphical tool for modeling dependent structures of high-dimensional probability distributions, and they have been proven to be useful and flexible tools in high-dimensional correlation structured modeling. And that's just a lot of words to say we can use this bind structure to model the high-dimensional distributions of correlation matrices and generate them. And specifically, we can use partial correlation binds to represent a correlation matrix. And there's different bind structures, how they look like, how they represent this high-dimensional model. And they include the regular binds, that is the picture that you see on the right. We have D binds and C binds that are ones we implemented in Mlfinlab. And from the picture on the right, you can see binds is just a graph structure that just, you have your nodes, you have your edges, and the edges just represent what is the relation between the nodes. And partial correlation binds, they measure the degree of association between two variables while controlling for a third random variable. And each edge in the bind is identified with a partial correlation coefficient. So you can take the values -1 to 1. And as I mentioned before, we have here on the bottom, on the left, we have the C bind, on the right, we have a D bind. And I guess you can guess a little bit why it's called the C bind, right? On the left, we have your nodes and your edges kind of look like the letter C. On the right, for the D bind, the nodes and edges kind of looks like the letter D. And you will see that, well, the C bind or D bind is not necessarily one better than the other. There's just like a different way to represent your data. And yeah, and we will use these two structures to generate correlation matrices. And the way that we do this is by traversing the partial correlation bind and calculating real correlation values from these partial correlation coefficients. And the partial correlation values are sampled from a beta distribution. And here in this picture, you can see how a correlation matrix generated with a D bind on the top and the C bind on the bottom looks like. And on the right, you will see the distribution of the pairwise correlation coefficients. And yeah, most likely you will see that it's a little bit similar to some of the correlation matrices that you might have calculated from your stock returns. The next method is the extended onion method. The way this one works is it iteratively creates a correlation matrix by starting with a one-dimensional matrix, and then you grow out the matrix by one dimension at a time. So the way you can think about it is you have your one-dimensional matrix, and you add layers to your onion one at a time until you create the correlation matrix of the dimension that you want. And this is possible because any correlation matrix of any size can be partitioned as a correlation matrix of a smaller size. So here in the question on the bottom left, you will see R represents the correlation matrix of dimension k plus 1. And that one can be represented by it's a smaller correlation matrix of dimension k, and Z represents a correlation vector. So if you combine these terms, you get the correlation matrix. And here on the right, you will see some example correlation matrices generated with extended onion method. And you will see it looks a little bit similar to Vine's extended onion the Vine's method. Next method for generating correlation matrices is the hierarchical correlation block model, or HCBM. And this model consists of correlation matrices that have a hierarchical block structure, where each block corresponds to a correlation cluster. And this generates an HCBM matrix that is defined as a set of nested partitions, where each partition is subdivided and partitioned again for a defined number of levels. And the correlation strength increases the higher the depth or the level. So here on the right, you will see a few HCBM matrices. You will notice that there are squares, that these are the hierarchical blocks in the matrix. You will see the bigger square contains smaller blocks, and the smaller the block it gets, the higher is the correlation strength. And one thing about HCBM, the picture here you see on the right, this is an idealized structure of the correlation coefficients. So if you have your model, your correlation matrices, you most likely never will see it looking like this, at first when you calculate it. So a way to make it a little bit more realistic is to compute one permutation of this correlation matrix and just outputting it in Mlfinlab. So you will see this correlation matrix on the right are the same ones as the one in the previous slides, just one permutation over. And that makes it look a little bit more realistic. And well, these matrices have the same correlation coefficients as the ones here in the previous slide. Our next method is bootstrapping, specifically the row, pair, and block bootstrapping methods. Just to recap bootstrapping really quick, bootstrapping is a statistical method to resample with replacement from a data set to create a new data set. And this new data set will keep the population and statistics of the original one, which is mean, standard deviation, mode, and etc. And it tends to lead to less overfitting in machine learning models, and is most commonly used in ensemble algorithms such as AdaBoost or random forest. And as I mentioned, the ones that we implemented in Mlfinlab are the row, pair, and block bootstrapping methods. So I will start with the row bootstrap. The way that this one works, it sampled rows with replacement from a data set to generate a new data set. And just the implication of sampling with replacement, this implies that the new data set can contain repeated data from the original one. So here, just to illustrate this, the picture that we have here on the left, we have the original data set of dimension t by n. And in Mlfinlab, this original data set is a correlation matrix. And on the right, we want to generate a new bootstrap data set, as also of size t by n. It doesn't necessarily have to be the same size. It could be a little bit different. But you will see that we have on the left, we have rows 1 through 100, columns A through Z. And then we use a random number generator to pick a random row from the original one and stitch it sequentially in the row bootstrap data set until we have all the rows that we want. And just one thing to keep in mind, like I mentioned, the row bootstrap data set doesn't have to be the same dimensions, but you also don't want to make it too small. For example, if you want to make a bootstrap data set of only 5 rows, it wouldn't really make sense because then you wouldn't keep the statistical properties of the original one. So that's just something to keep in mind. Next, I'm going to talk about the pair bootstrap. So this one is a little bit different than the row bootstrap. So in Mlfinlab, for the row bootstrap, you give it as an input a correlation matrix. For the pair bootstrap, the input is your stock returns. And how this one works, it samples pairs of columns with replacement from the original data set to generate a new one. And here on the left, we have a data set as well of size t by n. And remember, these are stock returns. So what we do is we have our columns A through Z and then rows 1 through 100. And we use a random number generator to sample random columns, I guess from A through C. Here on the right, in the top right, I have A, C, and the bottom B and C. So since we have my pair of columns, all returns, I can calculate a correlation coefficient, a single one from this pair of assets to populate the correlation matrix sequentially. And just to illustrate this, so this on the top, we have the original data set's correlation matrix that was generated from its stock returns. On the bottom, we have the pair bootstrap data set. And you will see it keeps the same structure as the original one, just the correlation strength changes at each correlation section. Next method is the block bootstrap. This one is a little bit more similar to the row bootstrap. And whereas in Mlfinlab, you use a correlation matrix as an input for the block bootstrap. And this one samples blocks of data with replacement from the original data set to generate a new one. And the block size can be of size equal to or less than the original data set. And to illustrate this, as I mentioned here, we have the original data set on the top, on the bottom left, we have size t by n. And in this case, our blocks are of size 2 by 2. So the way that is split up is we have rows 1 and 2, columns A and B is one block. Then rows 1 and 2, columns C and D is another block, and so on. So we split our data into blocks of 2 by 2. And the implementation in Mlfinlab, these blocks are non-overlapping, except on the edges if the data set cannot be evenly split by the block size. And again, we use a random number generator to get a block number, and we just grab the corresponding block from the original data set and just stitch it sequentially in the block bootstrap until we generate our new correlation matrix. And the last method for generating correlation matrices is CORGAN, or how to generate realistic financial correlation matrices. And I'll talk what makes a financial correlation matrix realistic in the following slides. So first question, how to generate realistic data sets. So given a data set, how to sample from its feature space. Here on the right, as you see, we have two faces, right? So you have a picture that is however many pixels. You can take the size, the value 0 to 255. So you want to sample only from the feature space of possible faces, not from all possible colors that however many pixels by pixels picture can take, right? So you don't want to sample from everything, just from the feature space of faces. So how do you do this? And there's various methods that researchers have come up with. One is autoregressive models. The next one is variational autoencoders and generative adversarial neural networks, or GAN. And actually, this is where CORGAN's name come from. And GANs have been able to produce really good results in a wide variety of domains. So like I mentioned, the picture on the right comes from whichfaceisreal.com. So only one of these faces is not real. So it just speaks how powerful GANs are from sampling from feature space and generate realistic data sets. So what makes a financial correlation matrix realistic? So researchers have been able to identify 6 stylized facts that the financial correlation matrices have that other correlation matrices don't have. And I'm going to go through them one by one in the following slides, but focus on the picture on the right. Again, we have a real correlation matrix and a CORGAN generated correlation matrix. So I guess you can read from the caption what it is, but if you didn't have a caption, most likely you wouldn't be able to tell all the time which one is real, which one is not. The first stylized fact for financial correlation matrices is that the distribution of pairwise correlations is significantly shifted to the positive. And to illustrate this, on the picture on the left, we have the CORGAN distribution shaded on blue. We have an empirical distribution shaded on red, and they're overlap with each other. And you can see CORGAN and empirical distributions are about the same. There's some discrepancies on the tails, but they look really similar. And if you contrast this, on the right is the pairwise correlation distribution of other methods, and you will see that it's not significantly shifted to the positive. It means it's almost 0. It has a lot of values in the negative. So that's one tell that the distribution on the right is not from a realistic financial correlation matrix. The next 2 stylized facts are that the eigenvalues follow the Marchenko-Pastur distribution, which means that there is a very large first eigenvalue that symbolizes the market. and followed by a few other large eigenvalues that symbolize the industries. So again, here on the left, we have empirical and Corrigan overlap with each other. You will see how similar they are. There's a really big value, the first one really big, followed by a few large ones, and it just eventually evens out. But if you contrast that with the eigenvalues of other methods, they're all just about the same. So another tell that the one on the right is not that realistic. The fourth stylized fact is that the eigenvector entries follow the Perron-Frobenius property, which means that the first eigenvector has positive entries. And the picture on the left, again, you can see how Corrigan and empirical overlap with each other, and all the eigenvector entries are positive. But if you focus on the right picture, you will see that for other methods, even though most of them are positive, you have some that are negative. So it violates that stylized fact for other methods. The next stylized fact is that the correlation matrix has a hierarchical structure of correlations. Here on the left, you'll have on the top an empirical correlation matrix, on the bottom a Corrigan correlation matrix. And the hierarchical structure basically is, if you remember from HCBM, it's kind of like the blocks or squares that form a hierarchical structure. And on the picture on the left, you more clearly can see it from dimensions 0 to 20. You will see some squares forming, some blocks forming. But if you compare it to the one on the right, you'll be able to see from other methods the correlation matrix doesn't have this nice hierarchical structure. It's a little bit harder to discern. And the last stylized fact is that the minimum spanning tree extracted from the correlation matrix have a no degree count that follows the scale-free property. And that means that the degree count of the minimum spanning tree decays following a power law. So we have, again, on the left, we have Corrigan overlap with an empirical distribution. And here we can see it starts really high on the left for Corrigan empirical and just quickly decays number of degree count. And if you compare it on the right for other methods, we don't see this quick decay. It just most likely looks like a linear decay. So it doesn't follow the scale-free property. Yeah, so this is what makes financial correlation matrices realistic. And you will see how Corrigan does a really good job to look like realistic financial correlation matrices. And I'm going to move on how to generate a synthetic time series. I'm going to start with the HCBM model. Just to recap really quick what the HCBM is, it's just composed of hierarchical block structures that are nested with each other. And the higher the depth or the level of the block, the higher its correlation strength. The way to generate time series from the HCBM matrix is to use a multivariate time series that either in Mlfinlab can either be a Gaussian or student's t distribution from the HCBM matrix. And well, you recognize the Gaussian is the standard random walk model, but that one doesn't capture tail behavior, I guess, too correctly. That's why we also offer the option, the student's t distribution, that is, it fits much better to real returns than the Gaussian distribution. And pictures on the bottom, you will see on the left, we have the HCBM matrix, on the right, the time series that were generated from the HCBM matrix. So if you actually calculate the correlation matrix from the time series on the right, well, as I mentioned, you won't see the perfect structure of the HCBM matrix, but you will have the same correlation coefficients. And if you do some clever operations, you can actually reconstruct the HCBM structure. But yeah, as I mentioned, if you calculate correlation matrix of the time series, you get the HCBM matrix correlation coefficients. And our last method for generating time series is how to generate correlated random walks, how to discriminate their distributions. And well, this method, the way it works is that you can imagine that you have multiple time series, and each time series has a length t. You got a time series with length t, and that time series is subdivided into k correlation clusters. You have t time steps, each divided into k correlation clusters, and those k correlation clusters are subdivided into d distribution clusters. So you can see you have like multiple embedded distributions in your single time series. And each correlation and distribution cluster can be generated with the normal, Laplace, or student's t distribution in Mlfinlab. And the way to visualize and split apart their underlying distributions is using the GMPR method, or the generic non-parametric representation. And I'm not going to go in depth in how that one works, but you can visit our codependence module in Mlfinlab for a deeper explanation of GMPR. And I'm just going to show pictures how GMPR behaves and how the time series look like. And the authors of the paper give us a a quick table of how to test a few correlated time series that you can generate. You have clustering that only has distribution dependence, or only the D distribution clusters, one with only dependence or only the K correlation clusters. And then we have a mix of both. I'm just going to go over them. So this is how the time series with only distribution clusters looks like. And actually it's 4 distribution clusters. On the left, you have the time series. On the right, you have the dependence matrix with using the GMPR distance metric. And well, GMPR does a good job of splitting apart 4 underlying distributions of the time series on the left. And here we have a time series generated only using dependence clustering. There's actually 10 dependence clusters in time series. You will see on the left the resulting time series. On the right, you will see the dependence matrix using GMPR, and you'll be able to tell how it splits apart the 10 distribution clusters. And the last one is a mix of both dependence and distribution. It actually has 5 distribution and 2 dependence clusters. You see on the left the time series, on the right GMPR that is able to tell apart these distributions. Just to conclude this presentation, synthetic data generation is a challenging field with many requirements. As we saw, we have to keep the structural properties, maintain privacy, you have to generate it quickly. Generating data that inherits properties of the original data is difficult, as we saw with our latest tools that are GANs and variational autoencoders, where we're barely able to keep all the original properties of the data. So this is really challenging to be able to generate realistic sample from the feature space of realistic correlation matrices, or even use realistic other structures. For example, there's also some work that has been done on using GANs to generate realistic time series that, still in the early stages. So that means that our current tools still need some work to make them perfect. As I've shown with Corrigan, there's some discrepancies on the tails of the distributions that Corrigan is not able to perfectly capture, but there's still some work that can be done, and we can, this is an evolving field and keeps improving. And our objective with Mlfinlab's data generation module is to close this gap and enable to augment your models. Yeah, and does anybody have any questions?